everyone. Am I audible, Shikha? In the previous class, what we have discussed, we were discussing what on now we are going to study. First of all, we will start the homework questions that I have given to you. I hope you have solved the questions. After that, we will move further. So what is the question I have given to you? Is this on your screen? Solve it. Am I audible now? Okay. So now coming back to the question, what it says, the question says there is a rectangular coil, dimension is given 5 and 2.5 centimeter. There are 100 turns in it. It has 3 ampere current in the clockwise direction is kept centered at the origin in the XZ plane. So first thing is that we have to draw a plane. That is, it is placed in the XZ plane. For example, let's suppose this is our x-axis, this is our z-axis. So y-axis is going to the into the plane. This is our XZ plane. And there is a rectangular coil, something like that. This is placed in the XZ plane. Now there is a magnetic field of 1 Tesla is applied along the x-axis. So there is a magnetic field B, which is 1 Tesla. If the coil is tilted through 45-degree about the z-axis. Now what is z-axis? Z-axis is given, as you can see, this is z-axis. Now, if this is the sheet and you want to shift it, then this will be about z-axis. If you shift it, it will be shifted like that. About z-axis, if you shift this sheet, it will be shifted in this direction. Like you can see my hand gestures like this. So if you shift this sheet by 45-degree, now focus on one thing. What is the direction of M? Everybody knows that tau is mb sine theta. Now, if you look closely in this particular diagram, it has a current of 3 ampere in the clockwise direction. It has some 3 ampere current in the clockwise direction. Now, if you shift it or tilt it, then the mm, angle which is made between magnetic field and the magnetic moment M and B, the angle will also be shifted by 45 degree, and ultimately final angle will be 45 degrees. So what you can write as tau is equals to MB sine 45. And if you put the values, what is M? M is NIA, you have studied in the previous class. B is the magnetic field, sine 45. Just put the values, and you can see that N is given as 100, current is given as 3 ampere. Area, you can see that dimensions are 5 centimeter and 2.5 centimeter. So you can place the values 5 into 2.5 into 10 raised to the power minus 4 into sine 45 is what? 1 by root 2. Now I have placed all the values. Your task is to just simplify it. And after simplifying, you will get the answer, and that answer will be approximately option A. If you solve it, you will get option A. So what's the main thing here? The tilting. When you tilt the diagram, tilt the coil, it will make 45 degree. Was the question asked in 2019. So I hope this is very much clear to you. You can solve it and get the answer. Moving further for the next question, which was given to you in the homework. So if I look closely at the question, one thing that is very much clear is a square loop is given, is carrying is some current I, and the magnitude of its magnetic dipole moment is M. Now, first of all, there is a square loop. So let's just draw the situation. There is a square loop. Let's suppose this is the square loop. Clear? And has some current I. Direction is not given, so you can take any direction, and it is a square loop, so you can take its side as A. I'm taking its side as A. Now, its magnetic moment is given as M. What is magnetic moment? Everybody knows that magnetic moment is NIA. So for square, what is given? Magnetic moment is equals to NIA, and it is given as M. There are no turns, only a single loop is there, one. Current is I. What is the area of this loop? This is a square loop, so area will be A square. So you can say that M is equals to I into A square. Let it be equation number 1. Now again, question says if the square loop is changed to a circular loop and it carries the same current, this square loop is transformed into a circular loop and carries the same current. The magnitude of the magnetic dipole moment of the circular loop will be. Now, first thing is you need to change this square loop into a circular one. So let's suppose when I convert it into the circular loop, what will be its radius? This is the first question, because when you calculate magnetic moment, you need area. For area of the circular loop, you need radius. So what I'm saying, let's suppose its radius is R. Let's suppose its radius is R. So if you take the radius as R, what is the thing which will remain constant? From square to circle, the length of the wire will remain constant. So what is the length of the wire when it was in the shape of a square? You can say that 4a is the length. Now, what is the length of the wire when it is transformed into a circular loop? You can say its circumference is 2 pi r. Is it clear? So what is the radius? 2 times it can be cancelled. So radius is 2a over pi. This is the radius of the circular loop. Now, what will be the magnetic moment? You can say magnetic moment, let's suppose it is m dash is equals to, again NIA, if you use n is 1, I into area of the circular loop is what? Pi r square, or you can say I into pi, and radius, if you square it, it will become 4a square by pi square. You can cancel out the things, so it will become 4ia square by pi. If you see from equation 1, I into a square is what? M. So you can place this value, and what you will get, m dash is equals to 4m by pi, which is option number A. So correct option is A. Now I will ask again, Meena has joined. Have you solved the questions given in the homework? I have given you two questions in the homework. This was the second one. Now I will start the new topic. One question is still remaining for the homework that you should continue after the class, and this is going to be your today's homework as well. So you can take the screenshot, and after that we will move further. Okay, done. Now, today's topic is work done in rotating the dipole or rotating the loop. This is again a very simple situation if you can understand. Let's suppose there is a loop. Have a look at the situation. There is a loop. This is a current carrying loop and it has some current, let's suppose I. And everything is simple. It has some magnetic moment M. Current is I, area is A. Everything is general, usually terms that we use, that the terms we use normally. So before moving, I just want to recall you one thing. JNV Rowing has joined. It's I'm repeating the same thing again and again, that you are joining the class very late. I don't understand why you are joining late. So before moving to the topic, I just want to recall one thing from electrostats or from this chapter. One thing is that when there is a current carrying loop, it behaves as a dipole. Do you remember the punchline that we have used in the previous lectures? What was the recall I am telling you? Current carrying loop behaves as a dipole. Now you can remember this is the magnetic dipole, obviously. Now you can remember from electrostats, there is a electric dipole as well. There was a electric dipole as well. If you can recall from electrostats, what was that? The combination of negative Q and positive Q charge, minus Q and positive Q. If you can remember this. How many of you remember the electric dipole? That minus Q and positive Q. This is an electric dipole. Now, when this dipole is placed in a uniform electric field, it experiences some torque. And if you want to rotate the dipole, you need to perform some work. In which direction, if you want to rotate the dipole? Opposite to its actual sense of rotation. So, work done that you need to do there was work done is equals to P into E cos theta initial minus cos theta final. I hope you can remember this relation. Is there anyone who can remember this relation from electrostats? Now, in the same way, if I talk about, let's suppose this is the loop, it behaves as a dipole. Now, if you rotate this dipole, let's suppose you are rotating, the field is into the plane, and you are rotating this dipole something like that. Can you see that dipole is rotated inside? So in this situation, work done will be, again I am saying, work done will be the dipole moment in this situation in magnetism is written as M. Electric field can be replaced by magnetic field, and the same thing is cos theta initial minus cos theta final. Now there might be a doubt, sir, what is theta initial and what is theta final? So I am explaining what is theta initial. Theta initial, or this theta is the, I'm talking about this theta only, initial angle between magnetic field and magnetic moment. I hope you can remember this thing. What is theta initial? Is the initial angle between magnetic field and magnetic moment. What is theta final? The final angle between magnetic field and magnetic moment. I hope this point is clear. So what is the good practice? You can make it as a box and you can remember this formula. Whenever they are asking the work done in rotating the loop, you can use this relation. Theta I is the initial angle, theta F is the final angle. Is it clear? Moving further for the next topic. Now, the next topic is galvanometer, which is again very important. It comes in the instrument section. So, lot of questions were asked from the instrument section in the NEET exam and the JEE main exam. So, let's try to find it out what is galvanometer. So, first of all, in one statement, if I say what is galvanometer, galvanometer is a device which is generally used to detect the presence of current in the circuit. I am not talking about to measure the current. It is used to detect the presence of the current, nothing else. It will detect the presence of the current only. JNV Rowing and Meena, is it clear? What it is used for? Used to detect the presence of current in the circuit. Clear? Now, how it looks like. So this is the construction part I am showing you. Just focus on that. So one thing is there are two magnetic poles. One is, let's suppose, North Pole and another is South Pole. Next is, between these poles, there is a coil of certain turns. Let's suppose there is a coil of n turns. Can you see that? There is a coil of n turns. And one turn of it is just attached to a torsion head. One end is attached with a torsion head. And one more thing, this strip that you can see is of phosphor bronze. phosphor bronze. I will tell you later why it is used of phosphor bronze only. The next end of this coil, if you wrap a coil, there will be two free ends. One end is attached to this torsion head, another end is attached with a spring like this. And this spring, now after that, this end is given to a terminal T1 and this end is connected to a terminal T2. So what are these terminal T1 and T2? These are the only two external wires that we can see. Only these two external terminals through which we can connect our circuit. So what are the two external points through which we can connect our circuit is T1 and T2. Next is inside the coil, there is a ferromagnetic material. Or if you don't know what is ferromagnetic material, I am just saying it, a soft iron core. This is a soft iron material. Or you can simply say it is a iron cylindrical shaped iron body. Now, one more thing in the circuit, there is a mirror placed at this wire, attached to this wire or this strip, which is phosphor bronze strip. There is a mirror. Now, this complete setup is placed inside a vacuum box, or you can say inside the glass box. Only T1 and T2 are the terminals which are outside the box. Clear? Now, one thing which is very important, I will tell you the things about this galvanometer. I hope construction is very much clear. What are the important things? The first important thing is the radial field. What is radial field? One thing you can remember for everything. I am not talking about radial field only. I am talking whenever you see the word radial. Radial means a field or any quantity which is directed towards a point, or that point is generally known as central point. Anything which is directed towards one point is known as radial. So in this case, what's happening? This is north pole from which field lines will emit. This is south pole at which field lines will terminate. Now the thing is, all the field lines will be directed from north pole towards this small ferromagnetic material. And from this, they will diverge again towards the south pole. So field lines will something look like, I can draw. They will something look like that. These field lines will be directed towards north pole, from north pole to this ferromagnetic material, and from this ferromagnetic material to the south pole, like this. And in the whole scenario, what is the benefit of this radial field? So let's talk about the benefit of this radial field. These are the two very basic fundamental questions that can be asked in certain region questions. So one thing, what is the benefits? After that, I will tell you how to make the field radial and how we made it radial. Benefit of this is, okay, just remember, if you can see my hand gestures, let's suppose this is the magnet, North Pole. And from every section, field lines are coming perpendicular to the surface. So this is a concave shaped magnet, North Pole. So field lines are coming perpendicular to it, perpendicular to it, perpendicular to it in this way. That means from x-axis to every direction, there is a magnetic field line. Directed from x-axis or starting from x-axis, the field lines are very variable in all the directions. They are available in all the directions. So what is the benefit of this? The magnetic field is parallel to the coil at, this is at every orientation. of coil. Now, by it doesn't matter at what position coil is. If you can rotate the coil, but every time you will see that magnetic field is parallel to the coil. Now, just answer me one thing. In that situation, if coil is parallel to the magnetic field, what will be the angle? I am waiting for your response. What will be the angle between magnetic moment and magnetic field? What will be the angle? Can anyone tell me? Cuckoo is there, Nina is there, Janvi Rowing is there. Can anyone tell me? If you don't know the answer, you can say yes or no. How would I come to know that? Okay. Were you present in the previous class, Cuckoo? I am assuming that nobody is able to answer the question that what will be theta. Listen, I'm just giving you an example. I will delete this. For example, this is which is placed in XY clear and magnetic field is parallel to it. That means magnetic field in the direction or in the y direction. Try to understand each and every word. If magnetic field is parallel to the coil, that means magnetic field is either in the direction or in the y direction. Both in both the cases, magnetic field will be parallel. Now, what is the thing you are supposed to find the angle between magnetic field. Magnetic field you know is either in the x or in the y. But whenever you find a coil, a current carrying coil, obviously I am talking about, the magnetic moment will always be perpendicular to it. Are you getting my point? Magnetic moment will always be perpendicular to it. So if the coil is in the xy plane, in which direction will the magnetic moment be? What will be the direction of its magnetic moment? Can you answer now? I am just talking about the magnetic moment direction, not the theta. And be responsive, be quick. We don't have a whole day. You again have the option to say no. I will not move inch ahead from this. You all have the tabs, so you can easily type. It's not like you are not able to type or type. You are using the screen of the school. You are using the tabs. I know that. So you can easily type. I am repeating my question again, repeating each and every term again. What was the term? Coil is in the XY plane, and the punchline was magnetic moment is always perpendicular to the coil. Then tell me the direction of magnetic moment. In which axis the magnetic moment will be? If you can't answer this simple question, then leave the class. I don't need such guys in the class. Leave everyone. The simplest of question you can't answer. Keep waiting. I will keep waiting. You will keep. You just stay like that. I am not going to move a single topic. My voice is completely clear. I can hear my voice as well. I'm writing my question. If your network is not good, I'm just writing my question. What is the direction of magnetic moment? I am just writing my question if my voice is not clear to you. Again, I am saying you have the option to ask, but you can't sit like that. You can ask me, sir, repeat. I will repeat, but it's not like you are sitting like that. Okay, somebody has answered. JNV rowing is saying south to north. Okay, now listen. Whether answer is wrong or right doesn't matter. I will make it correct, but you should answer, na? Your task is to answer. I will make it correct. What I was saying that coil is in the XY plane and magnetic moment is perpendicular to it. So magnetic moment, if you say perpendicular, this is already in the XY plane. So perpendicular axis remains Z axis. Moment will be in Z axis here. Magnetic moment will be along the Z axis. Magnetic field is along X axis. You can see what is the angle theta. Theta is going to be 90 degrees. So what I was saying that if magnetic field is parallel to the coil, then every time theta will be 90. Every time theta is going to be 90. This is the benefit of radial field. Now again, how the radial field is achieved, this is again very famously asked question in the NEET examination. In the assumption and revision questions, how to achieve radial field. So if you see clearly, I am telling you one or two ways to achieve the radial field or how it is achieved. First point is you can achieve it by using concave shaped poles. Remember, iron core by using soft iron core. you can achieve all, you can achieve in these situations. So that's what visible in the diagram. I hope voice is clear now. Okay, moving further. Now listen to me again. The working of this galvanometer. Try to listen very carefully. This is North Pole, this is South Pole. I hope you can listen very carefully to all the punchlines. So whenever this T1 and T2 are connected to the and this, I am assuming circuit has some current and current is passed through it like that. So whenever the current is passed through a coil which is in the magnetic field already, and the magnetic field is created by this north and south. So what can you answer whenever the coil is in the magnetic field has some current, some torque acts on it. Due to this torque, the coil is what the torque acts on it. Due to this coil starts rotating. Starts rotating, you can see that there is a strip. This is the which is connected to it. You can imagine like you have some uh, polymer in it which has some in it. And if you try to rotate the polymer, you can feel that certain it will try to come back. It will try to come back and you feel this tension. It will try to come back. Similarly, what will happen? This due to this body strip attached so rotates and some twists are generated. So to this Sorry for this interruption, students. What I was saying, when current, this coil rotates, and when it rotates, the strip attached to it, this strip also rotates, and torque is generated. Storing torque, what will happen after a certain some 40, 35-degree rotations, the restoring torque becomes equal to the original torque, and ultimately the coil is and it comes in equilibrium. Saying coil rotates and restoring torque generates. So try to remember the flow chart I was drawing. Torque is generated. Due to this restoring torque, equilibrium is achieved. So try to equilibrium is achieved, and if in the same time this mirror which was attached to the strip, when this strip get rotated, mirror will also rotate, and the image formed by to some other point, and you can clearly judge that there is some current, because if there is current, only then the mirror will be, only then the image will be shifted. There was some current, but you detect that there was some current. Just belongs on the principle of torque. So what is the principle here? Is the torque. If you can see further, the torque generated in the coil becomes equal torque, and restoring torque is rotated by some angle theta. Torque will be k theta that you have. So torque will be k theta, where theta is the angle twisted and k is the torsional constant. The torque acting on the coil will be I A is equals to k theta. Will be what? K divided by you here NAB into theta. You can see that in this whole term, K is the torsional constant turns in the coil, and A is the magnetic field which is created by north and south pole. These terms are generally known as, the combined group is known as galvanometer constant. So you can see that I is proportional to theta. What does it mean? It means that more the current, more will be the deflection. This is the simple. You can write down this formula. This is very important. You can. Now we will move further. Current sensitivity. Two important parameters questions are asked is current sensitivity. And what is current sensitivity? The deflection produced in the galvanometer per unit current. What does it? This is the galvanometer on the previous slide. Unit current. If you pass a unit current in this galvanometer, the amount of deflection it produces is called as current sensitivity. It will be more sensitive amount of current, and the deflection produced is very large. So you can read the deflection. You can find the deflection. That is called more sensitive galvanometer. So what is current sensitivity? produced in the galvanometer per unit current. How it can be written as in terms of formula? Current sensitivity is denoted by IS, can be written as deflection per unit current. Very simple relation. Deflection per unit current. Now, can you tell me the unit which can be formed? What will be the unit of current sensitivity? Either in radians, you can say divided by ampere. So unit can maybe radian per ampere, or listen to me now. This time, listen to me very carefully. It can also be measured. You have seen galvanometer in your schools. It is something like that. Hope you have seen it in your school. This is galvanometer. This is 0 mark. This is 1. This is 2. This is something 3. And there are certain divisions in them like this. So can you see that? Like I am saying, the needle is found to be here. Can you see that how much deflection? 1, 2, 3, 4, 5. So you can say that 5 divisions is the deflection, or you can say here 10 divisions is the deflection. So deflection can also be measured in terms of divisions. So one more unit which can be formed here is divisions per ampere. Is this clear? What is current sensitivity? Now, what can be the formula theta over I we can use? So you can see on the previous slide, this is the relation of I and theta. Right, for theta over I, so theta over I, if you transfer, it can be written as NAB over K. I hope you can transfer things, NAB over K. So what is theta over I, or what is IS? NAB over K. This is current sensitivity. Is it clear? Now, current sensitivity can be increased. You know that it should be high. The current sensitivity of a galvanometer should be high, but how it can be increased? So you can see increased by, from this relation, can anyone tell me how the current sensitivity can be increased? Very simple question I'm asking here. How it can be increased? Anyone who wants to answer? Okay, without wasting much time, I'm telling you there are various ways you can increase the current sensitivity. Like if you increase number of turns, if you increase area, if you increase magnetic field, or if you can decrease K. What is K? Torsional constant. Now, out of which the torsional constant of phosphor bronze material is the lowest. That's why I bronze material in the form of strip. Can you see that? Phosphor bronze material was used in the form of strip because it has lowest torsional constant. I hope this question is clear. Why phosphor bronze is used? Now, one more thing I will ask. The number of turns and area. If you increase the area of the coil, the size of the galvanometer will become bulky and it will not remain portable after a certain point of time. So we are not using larger area of the coil. Now again, you cannot increase number of turns to a certain limit or after a certain limit. Why? If you increase number of turns, that means length of the wire will increase. So N cannot be, area cannot be increased beyond a limit. So what are the two basic things you can change? Magnetic field and torsional constant. I hope you will try to remember. One more thing, I will end the topic here. What is voltage sensitivity? Voltage sensitivity is same definition you can use, but the term is per unit applied voltage. The deflection produced in the galvanometer per unit applied voltage. And if you use this relation, what you will get, Vs is equals to deflection produced, that means theta, applied voltage. Let's suppose you have applied some voltage V. Now again, if you apply some voltage V across the terminals T1 and T2 that you have seen on the previous slide, from the Ohm's law, you know that V is equals to IR. So it can be written as theta over I into R is what? R is the resistance of the wire in between. So in between there is a coil, and this coil, let's suppose, has some resistance G. Has some resistance G. So what is voltage sensitivity? Theta over I into G. Theta over I, you can see that it is current sensitivity. So Vs is equals to current sensitivity divided by resistance of the coil for you. And I will write it here. What is G? G is the resistance of galvanometer. Now, that's it. These were the two things that you should know. After that, I will just give you one question as a homework. There is a question on your screen. If you can answer right here, you can answer. Otherwise, it is a homework because we are done with the time. Screenshot, and once you take the screenshot, you can say yes, sir. And try to remember one thing. If you can take it as a warning that when you come in the next class, you must have your homework with you. You must try to answer. If you have some shortcomings, you can't type, you can't do, then try to overcome those things. Very good, Meena. Now you are responding. I need responses from your side every instant of time. Only after that I will teach. Otherwise, we are not going to continue these classes. Try to utilize the things to the full. Right now, ending the session.